And the last type of question that still falls under this, I guess, application would be, let's say mu is equal to, let's just keep it simple, mu is equal to 100, standard deviation is 15, and let's say I ask what percentage is in between 122 and 92. Okay, and I want to know how much is in between 92 and 122. Is that okay? And so to answer this, we're going to do this in two parts, okay? So the first one, whoops, we're going to find let's see if I can get this right. Okay, I'm going to try to get the area to the left of 122. Find this area first. Okay, and then I'm going to find the area to the left of 92 and say this thing is equal to this area minus this area. Okay, so we do, if I find the area to the left of 122 and I subtract off the portion to the left of 92, then what I will be left with is what's in between. And this is what I want, right? From 92 to 122. I don't know if you guys can see that. Does that kind of make sense? Okay, and so first we're going to find area to the left of 122, and then we're going to find the area to the left of 92, and then we're going to take the difference, okay? Okay. So the area to the left of 122 we actually did earlier, but we're just going to do z is equal to 122 minus 100 divided by 15. I get a z-score of 1.47, which gives me an area to the left of 0.9292. I do the same thing for 92. Z is equal to 92 minus 100 divided by 15. I get a z-score of negative 8 over 15, so I get negative 0.53. Z-score of, oops, negative 0.53, and the area to the left of negative 0.53, if I look this up in my table, gives me 0.2981. Okay, to do. Okay, so I get 0.2981, and so the difference is going to be 0.9292 minus 0.2981, and I'm left with something else. 0.9292 minus 0.2981, 0.6311. Okay, so this area here is going to be 0.6311. Maybe I'll draw like a little black line here. Okay. Okay, are there any questions on this? Okay. So then we have the reverse, okay? So I could say the mean is equal to 100 and the standard deviation is equal to 15, and I can say what is the score of someone in the 25th percentile. Okay. So, are you guys familiar with percentiles? Okay, 25th percentile basically means the value where 25% of the data is smaller. Okay? The 43rd percentile is the spot where 43% of the data is smaller. Okay? So the xth percentile is the spot where the x percent of the data is smaller than that value. Okay? Smaller values. Okay, so when we say, what is the score of someone in the 25th percentile? What essentially we're saying is that, if I were to draw a picture, okay, I'm shading in a spot, and I want to know what is this value so that the shaded area is equal to 0.25. Okay, so we still have a mean of 100, and I just want to know what is this score so that the shaded area to the left is 0.25. So essentially I'm going to just work backwards. Okay, so we just work backwards. So we first go to the table and find the z-score that is associated with 0.2500 or whatever is closest to that. So we want to find the spot, the z-score that's going to give me an area of 0.25 to the left. So I go to the table and I'm going to be in the negative side, right? And so the number that's closest to 0.250, it looks like I've got 0.2514 and 0.2483. Okay? And of these two values, if I were to, I got this one and I got this one. And if we ask which one is closer to 0.25, this one is, okay? And so what is that? What is the z-score there? It's z is equal to negative 0.67. Z is equal to negative 0.67 gives me an area of 0.2514. Is that okay? So from the table, we see that z equal to negative 0.67 gives an area of 0.2514. So we use that. We will use that. Okay? And so now we just go, okay, well, if z is equal to negative 0.67, let's turn that into a score. Okay. So what score gives z equal to negative 0.67? Well, we can just work backwards with the z formula. We have z is equal to y minus mu over sigma. So I'm just going to say z is negative 0.67. That's equal to the y, which we are looking for, minus the mean over the standard deviation. So I multiply this and I get negative Negative 0.67 times 15 gives me negative 10.05 equals y minus 100. And so that gives me y equals 89.95. So the score here, practically 90, 89.95. What is the score of someone in the 25th percentile? 89.95. Is that okay? So you should be comfortable working with that. There is a section in the book, section 4.4, talking about assessing normality. Okay? And basically, the question is, if we have data so given a set of data, can we conclude that they might come from a normal distribution? Okay, and the answer to this is it's complicated. There's no real good way to do it, okay? So one simple method is using the empirical rule, right? Empirical rule says what? 68% within one standard deviation, 95% within two standard deviations of the mean, and 99.7% within 3 standard deviations of the mean, okay? And so basically, you know, you're going to have a set of data. You've got, you know, rows and columns and et cetera, okay? And you can summarize these with y bar and s, okay? And then you can kind of do this crude check, and you just do, you know, y bar plus s and to, you know, y bar minus s. And then you say, is about 68% of the data points within this range? And if the answer is kinda, then that might kinda seems good, right? I mean, here you just have 3 kind of checks, right? And usually the one that's gonna be your biggest indicator of it might not be normal is gonna be this last one, okay? So essentially, if you go, you know, y bar minus 3 times s to y bar plus 3 times s, that should cover almost everyone, right? So let's say, you know, you do your, you gather your data, you take the mean, and you get a mean of 100, and you get s is equal to 20, okay? Right, you plug it into some summary thing, you get summary statistics. And so what it says is that if I go 3 standard deviations below, each standard deviation is 20, so if I go from 40 to 160, that should cover almost everyone, right? Almost everyone. You know, 99.7%. Okay? So if you have a data set of, you know, 200 data points, you should have essentially no one outside of this range. Maybe one person, okay? And if you're getting multiple data points, that might be a good indicator that you don't have a normal data set. Okay, so that's a crude check for doing assessing normality. Does that kind of make sense? And then the other one is using something called a normal probability plot. A normal quantile plot, also called normal probability plot. Now I don't want to get into the nitty-gritty of how these plots work, but essentially the basic point is, according to the normal distribution, something in the 95th percentile should have this z-score, something in the 80th percentile should have this z-score, and you're just going, and then you compare the actual z-score to the theoretic z-score, and if they line up and your data looks kind of like this, you get a straight line, this would indicate normality. And if you get anything that doesn't look like a straight line, so you get, data that goes like this, okay, not normal. and at this point, essentially, we're just eyeballing and doing rough approximations, or just rough ways of assessing normality. Okay, you can get more complicated methods of analysis into seeing if things are normal, and there's like the I forget, Smirnov-Kolmogorov thing. There's all sorts of tests you can do beyond the scope of this course. At this point, this is a good rough check, and then if you want to get a little fancier, you can do normal probability plots, and your book just talks briefly about those. Okay, and I think that's okay. I would say the biggest indicator that something's not normal is if you have really huge outliers, right? If you have something 4 standard deviations away from the mean, 5 standard deviations away from the mean, probably not normal, okay? Because normal, according to the normal distribution, almost everything should be within 3 standard deviations, and then there should be nothing that's like 6 standard deviations away. Should be. Of course, if you're getting stuff like that, it would be a problem. Okay, we're going to take kind of a step back or a step forward. There's this one section, so I choose to cover this one section in Chapter 5 today. Okay, and so there's one section in Chapter 5. And let me look that up, what it is. I think 5.4? Yes, okay. So 5.4, and this is the normal approximation to the binomial. Okay, so remember, the binomial distribution answers the question, I'm going to flip a coin 100 times. What's the probability that the coin lands exactly 50 times on heads? Okay? Or if I flip a coin 100 times, what's the probability that it lands heads exactly 51 times? Or something like that. Okay? Those are the types of questions the binomial distribution can answer. So with the binomial, we say, I flip a fair coin 100 times. What is the probability it will land on heads exactly 50 times? And so in this case, we would have n equal to 100, p equal to 0.5, and j equal to 50, right? And we would do 100, choose 50, 0.5 to the 50, 1 minus 0.5, which is also 0.5, to the 100 minus 50, which is also 50. All right. I'm hoping this looks familiar. Okay, so I did this quickly because I guess I'm assuming Okay. All right. What if I made this more complicated and I say same thing, but I flip a coin, flip a fair coin 100 times. And I ask, what is the probability it will land on heads 60 or more times? Okay, so in this case I have n equal to 100, p equal to 0.5, but what is j? J is 60, 61, 62, all the way up to 98, 99, 100, right? There's a total of 41 values here. And every single one of these would require me to do 100, choose 60, 0.5 to the 60, 1 minus 0.5 to the 40, plus 100, choose 61, yada, 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 plus 100, choose 62, all the way up to 100, choose 99, plus 100, choose 100, etc., etc., etc. Okay? This would be a lot of work to do by hand, and you will probably make a mistake somewhere along the way. Okay? And all of these values out here are going to be incredibly close to 0, that you won't even want to bother writing them down on paper. Okay? Well, I will show you how to answer this with the computer in a moment, but if you had to do this by hand, this would be a terrible thing to impose on you. Okay? So, let me just put a little disclaimer. These types of questions are now very easy to answer with a computer. Okay? But if we wanted to answer these questions by hand, we would need a better way than to do this. Okay? And so, this is when we use the normal distribution as an approximation for the binomial distribution. Okay? So we can use, so I'll say, when calculating things by hand, normal distribution will make our lives easier. Okay, so the binomial distribution looks like, you've got these, for large values of n and p, the binomial distribution ends up looking very much like the normal distribution. And this is not going to be a very good picture, but something like this, okay? And so you can kind of approximate it with the normal distribution, okay? Do you remember what, if n is equal to 100 and p is equal to 0.5, what is the mean and standard deviation of this binomial distribution? Do you remember? The mean is n times p, so we expect 50 heads, and the standard deviation is the square root of n times p times 1 minus p. So I get the square root of 100 times 0.5 times 0.5, square root of 25, which is conveniently equal to 5. Okay, is that all right? So what we're going to do is we're going to answer this question, this one. I flip a coin 100 times. Using the normal approximation. Okay, so we established that the binomial here, n is equal to 100, p is equal to 0.5, gives mu equal to 50 and sigma equal to the square root of 25 equal to 5. So this binomial distribution will have these properties. So we're going to approximate it with a normal distribution that have the same properties, okay? Approximate this binomial with a normal distribution with the same properties. Namely, a normal distribution with mu equal to 50 and sigma equal to 5. Okay? And in shorthand, we can just write n 50, comma 5. Normal distribution with mean equal to 50 and sigma equal to 5 is often written this way. All right, and so the question was, what is the probability it will land on heads 60 or more times? Okay, and so I'm going to put 50 in the middle, and I'm going to 60, and I'm going to just draw a line right there, and I'm essentially asking how much is greater than 60? Okay, and so this would give me z equal to 60 minus 50 over 5, z equal to positive 2. Okay. But wait, we have a slight problem, okay? And that is the normal distribution is continuous, but the binomial distribution is discrete. Okay? So in the normal distribution, there is no distinction between saying what is the probability that the height of a woman, you know, going back to our example with female heights in the United States, we could say there's no distinction between saying, you know, what's the probability that a woman's height is 61 inches or lower versus what's the probability that a woman's height is lower than 61 inches. Okay, so in the normal distribution, is continuous, so there's no distinction between probability that say y is greater than or equal to 60 versus probability that y is greater than 60. Okay, because it's continuous, we don't make a distinction between these two things. But the binomial is not continuous. Binomial is discrete. So there is a difference between probability that y is greater than or equal to 60 versus probability that y is greater than 60. Okay? And so what do we have here? What is the probability it will land on heads 60 or more times? That is equal to what? Probability that y is greater than or equal to 60. Okay? Because if I say what's the probability that y is greater than 60, the answer to this thing, going back to the previous page, I would not include this first one, right? It would just be 61 through 100 versus 60 through 100. Okay? So to take care of this, we have something called the continuity correction. This, so we use the continuity correction to account for this. Okay, so an important note, We use the continuity correction only when you're trying to approximate something discrete, like the binomial, with something continuous, okay? If you're just dealing with normal distribution stuff, don't use the continuity correction. You only use the continuity correction when you're trying to approximate the binomial with the normal or some other discrete thing with the normal distribution, okay? Use the continuity correction only when approximating a discrete thing with a continuous thing. Okay, don't use the continuity correction if you're just dealing with continuous things the whole time. There's no correction there. It's just continuous, it's fine. You don't have to use the continuity correction if I say, what percentage of women are shorter than 61 inches? There's nothing to correct. So what is this continuity correction? Okay, well, okay, so imagine we have this normal distribution centered at 50, and then we're going out, let's go over here, okay? We're going to 60, and imagine the underlying binomial distribution with a bar like that, okay? And imagine another bar, so this is not to scale, but I think it's okay. I've got a bar right here centered at 61. Okay, and then another bar at 62, and over here 59. So just imagine we've got all of these bars, okay, from the histogram. Okay, and so the question said, you know, what is the probability the coin lands heads 60 times or more? Okay, so if I were to shade these in, it's going to bother me over here. Sorry. Okay, so if I wanted to shade these bars in, okay, 60 or more means I would shade in this bar for 60, right? I would have this bar shaded in, and I have this bar shaded in. Et cetera, et cetera, et cetera, right? So I would shade this one in just like that, okay? So essentially, where am I drawing my cutoff line on this number line? Not at 60, but where? The shaded areas that I'm drawing a cutoff at 59.5. Okay? And so the continuity correction is a factor of plus 0.5 or minus 0.5. And the book kind of tries to explain, you know, use plus 0.5 here and minus 0.5 there. For me, I think it's just best to draw the picture and decide if you want to include this bar, okay? So if I say, what's the probability that the coin lands heads 60 times or more, the cutoff is going to be at 59.5. If the question was, what is the probability that the coin lands heads more than 60 times? Where would our cutoff be? 60.5, okay? So this is This one corresponds to probability that y is greater than or equal to 60, and over here we've got probability that y is greater than 60, okay? So in that case, we don't want the bar shaded for 60, and so we would draw the cutoff at 60.5. Okay, so but anyway, for this problem, we established that the cutoff is 59.5, and we're approximating it with the normal distribution. And so we would have z is equal to 59.5 minus 50 divided by 5. And then you solve the problem just as if it were a regular old normal distribution problem. Okay. Does that make sense?
Why is it cut
No.
off 0.5?
It's 0.5 because 0.5 is half of one discrete unit, okay? So in the discrete distribution, the coin can land heads 58 times, it can land head 59 times, it can land heads 60 times, okay? And it is different if we say 60 times or more versus more than 60 times. And so you have to imagine that we have a bar centered at that number. And you want to ask, do I want to include this bar, yes or no? And in this case, we do want to include the bar. So in drawing our picture, I'm shading in 60, I'm shading in 61 and everything above that. By shading in the bar centered at 60, my cutoff is not at 60 itself, okay? It's not down the middle here. It is at 59.5, okay? It's halfway between 59 and 60, okay? Because the bar centered at 59 goes from 58.5 to 59.5, and the bar centered at 60 goes from 59.5 to 60.5. And we want to include the entirety of that bar, so my cutoff is at 59.5. If I wanted only to go for a y greater than 60, I wouldn't include this, and so I would just, I don't know, maybe I'll shade a different color.
I just don't understand why it's 59.5 versus like 59.99999.
Because 59.99999 is essentially 60, and so you have to imagine these discrete units, because the underlying distribution, we're trying to approximate the binomial, right? And the underlying distribution, the binomial distribution, says it can either be 59 or 60, nothing in between. And so you're going to split the difference between those and get 59.5, okay? In the continuous distribution, we don't make a distinction, okay? Because greater than 60 and 60 greater than or equal to 60, essentially the same thing. So, is that okay? Or
Yeah.
On the other student, you have,
I don't know. Maybe I could just read about it.
okay. Okay. Don't hesitate to ask questions. So we'll end this section here, and I'm going to go into covering some details of the lab assignment. Okay. So we'll pause this